In this lab, we will compute all pair similarity estimators based on MinHash signature. We will compute all pair similarity for number of hash functions 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Let's display the signature matrix that we had and the transports of it. So what happens is that this is the signature matrix that we had for the number of hash functions equal to 10. And transpose of this signature matrix is where the rows will be the column and the column will be the rows. So you can see that this first row 92, 51, 83 and so on to 255, 104, 122 is the first row in the transpose matrix. Okay, so from scip dot special dot distance import pdist comma square form. The length of the transpose of signature matrix is 3430. This is just showing the calculation. Now, the square form of 1 minus p distance of np transpose signature matrix, comma, matching, and we want the diagonal to be 1. So this is how it looks like. So what happens is that so we have the transpose matrix, and now let's show what this function does. So p dist bracket np dot transpose of signature matrix, comma, matching gives 0.97, 0.99, 0.94 and so on to 0.7, 0.96, 0.78. So what it has done is that it has calculated the probability of the distance between the values. So yeah, so p distance, it calculates the spatial distance between the columns. So the first column and the second column, the distance is measured and put in this place over here. So say let's see what was the length of the signature matrix. 100. So this p distance, so when we transpose signature matrix, there will be 100 columns. So this probability of the distance, these values should be 100. So let's see the size of this array. Yeah, so length of the distance is 588,735. So it has calculated the p dist has calculated the probability of the distance between every pair, and that's 588 5,888,735 values. So all these, so let's do 1 minus these values. So we will do set one cell, and we will just copy and paste this, and we are doing 1 minus. Let's see what it gives. So 1 minus, so what it does is that 1, and it subtracts each of these values from 1, and the result is here. And when we want to show the square form of this, then let's see. Let's insert another row above. Square form. Square form is the function that we have imported from scipy.special.distance. And it gives this one. So a square form of 1 minus p distance is this one. And the length, let's see the dimension of it. So let's see the number of rows fetched. 3,430. That's the number of documents. And let's see what is the, let's transpose that array, that matrix, and find the number of rows. And that will be the number of columns of the original square form matrix. 3,430. So, so a square form forms 3,430 by 3,430 matrix. Let's see. Let's do this. 3,430. Let's find the square of it. How many values in there? So 11,764,900 values in there. Okay. And if we divide that by 2, so 5,882,450. And the length of this array here is 5,880,735. Okay. Let's see. Now, and if we let's print that. Let's see what this matrix looks like. Let this be equal to similarity estimate, and if we do np.fill_diagonal, of similarity estimate with 1, then 1 gets filled in the diagonal. And when we print similarity estimate, you can see that 1 is printed in the diagonal. And this is a symmetrical matrix. You can see that along the diagonal, you can flip this corner onto this corner, and the values will be same. Now the Jacquard similarity matrix is this one that we already found, and length of similarity estimate. Okay, so we don't need that. Now, what does this function do? So this function over here, I'll show you what it does. This function, what it does is that it takes the similarity estimate matrix, which is this one, and then it subtracts the Jacquard similarity matrix to find the difference. Okay, so and that you can do by similarity estimate matrix dot double underscore. This is double is underscore sub double underscore and bracket Jacquard similarity matrix, and it gives this one. Then we write the definition of compute similarity estimate, because in this lab we are computing similarity estimate. Let the length of the signature matrix be number of hash functions. So number of hash functions equal length of similarity matrix. So transform equal np.transpose of signature matrix. So we take the transpose of the signature matrix. Similarity estimate equal square form of 1 minus p digit of transform matching. Then we do np.fill underscore diagonal of similarity matrix with 1. Retain similarity estimate. Definition: calculate mean average error. So we also want to calculate the mean average error. Bracket, similarity estimate is 1 matrix, comma, Jacquard similarity matrix. And that function is let number of dots equal length of similarity estimate. Then we retain np.sum of absolute value of similarity estimate minus Jacquard similarity matrix and divided by number of dots squared minus number of dots. So number of dots squared is the size of the matrix, which is n by n. So it's a square matrix. So that's why number of dots multiplied by number of dots. And number of dots is the length of similarity estimate. And we subtract number of dots because we don't want to include the diagonal. The diagonal is filled with 1. Now, in this command, we are just showing the working. For number of hash functions in range, bracket 10, 101, 10, print number of hash functions that will print 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. The distance between two consecutive values is 10, and it goes up to 100. Okay, now in this we write another function, generate hash function. we have already done in the previous lab, but let me go through it again. Definition to generate hash function of number of words. So P equal 999983, I equal random dot rand int from 0 to P minus 1. So that will give you random integers. And so this will give you a random integer, and if I run this again, it's going to give me a different integer. So B equal also random dot rand int from 0 to P minus 1. Definition, hash function of x. Now x we don't know, and x, whatever values you put in here in place of x, it will retain I, which is the random integer, multiplied by this x, which is unknown, and we have to feed in the values, plus b, which is another random integer, and mod p. So mod p is 999983. This is a chosen value. Now what it returns is that a division by p, and then there is a remainder, and that remainder is divided by number of words, and then the remainder, and it returns the hash. So this function here returns the hash function where x is unknown. Okay, we write another definition to generate hash functions. Feed in number of hashes, comma, number of words. Retain, generate hash function, which is calling this function with the number of words, for underscore in range number of hashes. So the number of hashes, for example, if we put number of hashes equal 20, then the range will be from 0 to 19. So there will be 20 hash functions. And so this generate hash function will be generating the hash function 20 times. So one hash function is produced, and then the next one, and then the next one, until 20 hash functions are produced. Then we compute the MinHash signatures for all documents. Definition, compute signature matrix of hash functions, comma, words per doc. So we input hash function into this definition, and words per doc. Words per doc is in a form of set, nested set, where the first value is the document ID, and the next set of values are the word IDs. Number of hash functions equal length of hash functions. So say if the length of hash function is 20, so number of hash functions will be 20. Number of docs is length of words per doc, and that will be number of documents. And signature matrix equal np.zeros bracket, number of rows is number of hash functions, and the number of columns is the length of words per doc, and that signature matrix will be filled with 0. For doc ID in range, number of docs. So number of docs is length of words per document, and that's number of documents. So range will be from 0 to number of documents. For hash function index in range, number of hash functions. So if the number of hash functions is 20, then the range will be 0 to 19. So hash function index will be from 0 to 19. Hash function equal hash functions bracket hash function index. So hash functions bracket hash function index. So there will be 20 hash functions, and the range is the hash function index is ranging from 0 to 19, and the SA hash functions of 10. So 10th hash function will be read for hash function. And signature matrix of bracket. So raw number is hash function index at 10, and bracket doc ID, say doc ID in range a number of documents, say let's see 3429. So 10th row and column is 3429. So the value will be minimum of all those words for word in words per document. So doc ID. So the ID is 3429. So the words per document. So the words for document ID 3429. So all those words will be hashed, hash function. So all those words, there is value, and that will be hashed. So using this hash function, and then the minimum will be found, and that value will go in the 10th row and column 3429. Retain signature matrix. Next, let's create the empty arrays. Hash function count equal empty array. Mean square area values equal empty array. Time taken equal empty array. Let's put a random dot seed of 1800. Now we're doing random dot seed because if we're going to get the values repeated for the same values, we will not get the repeated values. So for number of hash functions in range 10 to 101. So from 10, like here, from 10 to 100 with a distance of 10. Hash functions equal generate hash functions bracket number of hash functions. So say 10 comma number of words, and number of words we will feed in the number of words. So hash functions equal generate hash function, number of hash functions, which is say for example the first one will be 10 comma, and number of words will be what? Generate hash function of number of words, and number of words comes from let's see what's number of words. Let's insert that and number of words. So number of words is 6,906. So this 6,906 was already given in the original file. That's the number of words 6,906. So the words per document, where the first value is the document ID and the second set of values are the word IDs, and the number of words are 6,906. So let signature matrix equal compute signature matrix, and the input is hash functions and WordSpay document. So hash functions, after generating the hash functions, so we chose number of hash functions to be 10. So number of hash functions, 10 hash functions will be produced. So all those hash functions are put in here, and the WordSpay doc that is in the set form is put in here, and the signature matrix is computed using compute signature matrix using this function here. And then we want to measure the time. So we want to measure the time taken to compute similarity estimate. So let start time equal time dot time, open and close bracket, and let similarity estimate equal compute similarity estimate of signature matrix. Now signature matrix, we know that signature matrix is compute signature matrix, which is computed from here. So that signature matrix will be put into this function, that will be the input into this function, and the similarity estimate will be computed. So let's see what the function compute similarity estimate does. So it finds compute similarity estimate. It so it computes the similarity like this. It is a matrix. Okay. Now after that, let's finalize the time. Time taken dot append bracket, time dot time, open and close bracket, minus start time. So the time taken is measured like this, and the time taken is stored in this array. Then we measure the mean average error equal calculate mean average error. This is the function that we call. So remember, so calculate MAE, which is mean average estimate, and that is similarity estimate minus Jaccard similarity estimate, and all those differences, we find the positive value of that, and then we sum all the values and we divide by the size of the matrix, but we don't want the diagonal to be included. So then hash function count. So hash function count is an empty array. So we will append the number of hash functions. The number of hash functions, the first one is 10, the next one is 20, and so on up to 100. And MAE values dot append MAE, and MAE is the mean average estimate, which is using the equation similarity estimate minus Jaccard similarity estimate. This is what the function does, and then takes the positive value of that and then finds the sum of all the values and divided by the size of the matrix, the number of values in the matrix, and subtract the number of values in the diagonal. And then what we do over here is we find the running time of estimate of all pairs similarity based on MinHash with different values of number of hash functions. So we need this tabulate function. From tabulate, we import tabulate. So this is the library that we need, and we import that. So what we're doing over here is we zip hash function count and time taken. So in set zip hash function count and time taken. So these two arrays here, hash function count and time taken, we zip them. So they'll be together. The corresponding hash function count and the time taken will be together. The headers are number of hash functions, which is for hash function count, and time in seconds is for time taken. And then what we do is that we tabulate that. And we print it over here. We type print and we can see number of hash functions 10, 20, 30, 40 and so on, and time in seconds is given over here, and the lowest time taken is 0.211877 for 10 hash functions, and it increases, the time increases as the number of hash functions increase. Then we found a mean average estimate for and we put over in this array. So we will use that to plot over here. So plotting mean average estimate versus number of hash functions. So we need to import matplotlib.pyplot. So import matplotlib.pyplot has PLT, and plt.plot hash function will be on the horizontal axis, and mean average estimate values will be on the vertical axis, and let's label that horizontal axis to be number of hash functions, and we'll put D in the bracket. So plt.x labeled in the bracket, we have number of hash functions, bracket D. And Y label, we want it to be a plt.y label, bracket, mean absolute value, mean absolute error, bracket MAE, and we get this. So you can see as the number of hash functions increases, the mean absolute error decreases, which is a good thing, which shows that more hash functions decreases the mean absolute error. And then let's present those values in table form. So print, bracket, tabulate, bracket, zip, hash function count, comma, MAE values, comma, headers equal number of hash functions, and comma, mean absolute error, close the brackets, and this gives this. So the lowest mean absolute error is, as you can see, that as the number of hash functions increases, mean absolute error decreases, and the very small mean absolute error is for 100. Number of hash functions equal 100. Mean absolute error equals 0.0140912.